Welcome to section 6.1, areas between curves. We talked about areas briefly in section, I believe, 5.4, and we talked about area being the integral from A to B, top minus bottom. I want to expand on that today and also talk about integrating with respect to y. If you're integrating with respect to y, then over here is the top and over here is the bottom. So let's just do some setups and then we'll actually integrate. This first one, set up integrals, plural, for the area of the shaded region WRT. That means with respect to x. Do not evaluate. Okay, so we want top minus bottom. Top minus bottom. As we go from 0 to 2, the top curve is x squared and the bottom curve is the x-axis, which is y equals 0. So the area is going to be the integral from 0 to 2 of x squared minus 0 dx. No, you don't have to write minus 0. Plus, that takes care of this first part. Then I need the second part where the top curve changes. That's why I need two separate integrals. So plus the integral from 2 to this line crosses at 6. So 2 to 6. Top curve is negative x plus 6. Again, the bottom curve is the x-axis, which is y equals 0. So top minus bottom. And I needed two integrals because top curve changed partway through my interval from 0 to 6. And so if I clean that up, 0 to 2 x squared dx, wouldn't want to leave the minus 0 there, plus the integral from 2 to 6 of negative x plus 6 dx. And I stop there because I'm not supposed to evaluate. So do not evaluate means don't find antiderivatives and get a number for your answer, just the setup. Okay, same problem, but now we're going to integrate with respect to y. So instead of thinking vertical lines, I want to think horizontal lines. My top curve is over here. My bottom curve is over here. Now this will be an integral with respect to y, so I need to solve each of these equations for x. The first one gives me x is negative y plus 6, and the bottom curve is x equals root y. So a is the integral. Now I'm going to have those little lines going through that region from 0 to 6. No, sorry, 0 to 4. Because these two curves meet when y is 4. So up here, this is 4. 0 to 4. Top curve is negative y plus 6. Bottom curve is y to the 1/2 dy. So this is actually a more desirable integral because you can get the area, which is one integral, rather than two like you needed to with respect to x. Now I encourage you at home to verify that the area is actually 32/3. And you can do it by evaluating this integral or both of these and adding these two numbers. You should get 32/3 in each case. Okay, next one. Sketch and shade the region bound by these two curves. Set up an integral for the area of the region. Do not evaluate. So again, in order to, well, we don't have the sketch here. So the first thing I'm going to do is find out where these curves meet. So when you want to find out where two curves meet, you set them equal to each other. X squared is x plus 2. Move everything to one side and factor. X minus 2, x plus 1 is 0. So x is negative 1 or 2. So they meet at negative 1 at 2 and 2. The parabola I can easily graph. Y equals x squared when x is negative 2 and 2, y is 4. So that looks something like this. And then the line y equals x plus 2, it's got slope 1. It crosses the y-axis here. It meets the parabola here. So it goes like that. And it also meets over here when x is negative 1. So this is my region. It's a single region. So I can evaluate the area with one integral. And the integral would be integral. I'm going to go from negative 1 to 2 I'm going to integrate with respect to x, top minus bottom. The top curve is x plus 2. Subtract the bottom curve, which is x squared, dx. That's all I wanted to do was the setup. Okay, remaining two, we're actually going to find areas. First, find the area of this green region here bounded by sine x and cosine x. So the top curve is sine x, y equals sine x, and the bottom curve is y equal cos x. So the red one is sine x. And what is this value and what is that value? Because the area is going to be the integral from this value to that value of sine x minus cos x dx. So sine x equals cos x. The first place that happens in quadrant 1 is pi over 4, where they're both positive. And the second place it happens is over in quadrant 3, where they're both negative. So those are the limits on the integral, pi over 4 to 5 pi over 4. All right, and this time we are going to evaluate. So we're going to find an antiderivative. The antiderivative for sine is negative cosine. And for cos, it's sine, straight bar, pi over 4, 5 pi over 4. All right, there are going to be a lot of negatives, so be careful. So 5 pi over 4 is down here. Cosine of 5 pi over 4 is negative 1 over root 2. So this gives me 1 over root 2. And then sine of 5 pi over 4 is also negative, so plus 1 over root 2. And then I'm going to subtract the value at pi over 4. Cosine of pi over 4 is 1 over root 2, so that'll give me negative 1 over root 2. And then I'll have minus, again, 1 over root 2. Yikes. All right, so this minus, if I distribute it, I get plus plus. So I have 2 over root 2 plus 2 over root 2, aka 4 over root 2, aka, if you rationalize, that's 2 root 2. And everywhere I have a 1 over root 2, you could do the same calculations with root 2 over 2. A lot of students learn their unit circle with cosine of pi over 4, say, is root 2 over 2. I don't rationalize, I just write it as 1 over root 2. But they are indeed the same number. Okay, one more. Sketch the region bound by these two parabolas. Find the area of the region. Okay, x squared plus 16. Let's see, that's a parabola. It crosses the y-axis at 16. When x is negative 2, y is 20. And when x is 2, y is 20. So the first parabola looks like that. This parabola, y equals 5x squared, it's going to go through the origin, and it's going to come up like this. And it's actually, I'll show you, it intersects that other parabola at negative 2 and at 2. And so the way to see that, set the two curves equal. 5x squared equals x squared plus 16. Move everything to one side. 4x squared minus 16 is 0. Factor out a 4. X squared minus 4 is 0. That gives us x equals plus or minus 2. All right, so our area is the integral from negative 2 to 2 of the top curve, which is x squared plus 16, minus the bottom curve, which is 5x squared, dx. So I'm doing vertical lines, top minus bottom. Let's clean up. This is the integral from negative 2 to 2 of negative 4x squared plus 16, dx. All right, now I'm going to evaluate this integral, but I'll show you a quicker way in a moment. This is the integral of negative, well, we're actually going to integrate now, so I'm dropping the integral sign, I'm dropping the dx. Negative 4/3 x cubed plus 16x between -2 and 2. That's, if I put 2 in, 2 cubed is 8. So this gives us -32 thirds plus 32 minus, when I put -2 in, I get positive 32 thirds minus 32. Now, if I distribute, I get -64 thirds, and then distribute that minus sign, that gives us plus 64, which is 2/3 of 64, which is 128 over 3. All right, a quicker way, when you have a region that is symmetric with respect to, in this case, the y-axis, you can find the area of half the region and multiply by 2. So this integral here, this is actually equal to twice the integral from 0 to 2 of -4x squared plus 16 dx. These are the same number. This computes just the integral computes the area in quadrant 1, and then I multiply by 2 to get the whole area. The reason why that's desirable is it's always wonderful to have 0 as a limit. It just makes calculations much easier. So I wouldn't have had to do all of this minus stuff. Would have been much easier. Okay, and we'll do that next semester. That's the end of this section.